Today I'm excited to talk to you about ice boxes. They're also called ice tables by some people, and sometimes people don't use that terminology. An ice box, from back in the day, I've always loved ice boxes as a piece of furniture. My grandparents had old-fashioned ice boxes, which are these beautiful kind of wood cabinet-looking things with metal lining in them that you'd keep your actual ice in to cool things down, kind of precursors to refrigerators. So I like ice boxes kind of for the historical reference to them, but it's actually an acronym that helps us to solve for equilibrium concentrations in a chemical reaction. So if I know some information about an equilibrium, if I'm given a chemical reaction and I know something about the equilibrium constant, and I know how much I start with, then I can figure out how much I'm going to have at equilibrium, because we know that there's going to be a forward reaction that's occurring, so my reactants form products, and a reverse reaction that's occurring where my products form reactants, and these processes are going at an equal rate. That's the equilibrium part. So the rate of two opposing processes, forward reaction and reverse reaction, are the same, and when we get there, then we're going to have some reactants in there and some products. And how many of those we can answer with an ice box, which is kind of fun. Okay, so here's the technique. We can solve problems that look like this. I think it's actually just easier to work them in the context of a problem. So we'll kind of walk through the problem solving, we'll walk through the strategy. We'll do two examples here in this video. Okay, so what are the equilibrium concentrations for all reactants and products? So everybody here. And of course, everyone here that we can talk about the concentration for, so that would just be our gases and our aqueous solutions. Because recall, we can't talk about the concentration of a pure liquid or a pure solid. So we're going to start with 1 mole each of carbon monoxide and water. So I know how much concentration-wise I'm starting off with. I have 1 mole in 50 liters of each. So I'm going to have to do a calculation there to get my concentration. And I need that initial concentration for my first line. So my setup here, and hence the term icebox, is I'm going to start off with my initial amounts. I for initial. So if I take my 1 mole and divide it by 50 liters, moles per liter gives me molarity, then it means I start with 0.02 molar carbon monoxide and 0.02 molar water vapor. So I'm making a table here. I'm making a box, essentially. So here's my initial concentrations of these guys. Now, what are my initial concentrations of my products? Well, before the reaction is started, this is the initial part, then I have no products unless I'm given information about that. And sometimes you'll see that you'll actually start with some of these guys too, and that'll impact things, and we'll talk about that in future videos. But for right now, if we're just given information about reactants, then we know that there's no products yet, because initially these things haven't reacted together to produce these things. So we have 0 for these guys, no concentration of carbon dioxide or hydrogen. Okay, so far so good. Here's our initial information. The C in my icebox stands for change. So the change is going to come from the molar quantities that are reacting within this particular reaction. So my carbon monoxide, when we look at a chemical reaction, we can think about these as individual molecules that are reacting together, but more often chemists think about them in terms of the number of moles, these molar ratios that come from the coefficients. In this balanced chemical process, it's 1:1 and then 1:1 for my products as well. So my change is going to be in how much these are all going to go down, and they're all going to go down in the same proportionality because it's all a 1:1 ratio, 1:1 to 1:1. So my reactants are going to go down by a specific molar quantity, and I don't know what that is unless I'm given information, which we aren't. This one is going to go down by the same molar quantity, we'll just call that X. My carbon dioxide is going to go up by a certain molar quantity, and my hydrogen is going to go up by that same 1:1 to 1:1. If I had different coefficients here, that would change my X values, but because everything is 1, then it's a nice and easy change. Reactants were going down, products were going up by these equal proportions. Okay, so now we have our initial, we have our change, and at equilibrium, it's going to be the sum of these two values. I started with a certain molar concentration, I changed by a certain molar amount, so at equilibrium, I have my initial plus my change. I have my initial plus my change. Okay, so I'm just adding together my columns here in my little icebox. Same thing on my product side. Now I have my initial, which is 0, plus my x means that at equilibrium I'm going to have x concentration, x molar concentration. And same for my hydrogen because it's 1 to 1. Okay, so there's my icebox. And you might say, great, there's still a lot of variables in there still, right? But it's only one. It's really only one variable. And we have a way of relating these equilibrium concentrations through K. Our K value, our expression for K, gives us a way to solve for this X. And because we're given a value for our equilibrium constant here at our 0.58, then that's going to allow us to solve for X. So my equilibrium constant expression, so here's my Kc, that's going to be equal to the concentration of my products over the concentration of my reactants. So the concentration of my carbon dioxide times my hydrogen divided by the concentration of my carbon monoxide times my water vapor. And again, I'm including all of them. It's a homogeneous equilibrium that includes all gas phases, so I can talk about the concentrations. Now these guys, I now have equilibrium concentrations for, and that's what I'm solving for. So now I can plug in my variables. My concentration for carbon dioxide at equilibrium is X, and my concentration of hydrogen at equilibrium is X. At equilibrium I have 0.02, whoops, forgot my 2, molar minus X for my carbon monoxide, and for my water, 200. Okay, so I have this, which is equal to, let's kind of combine some terms together. Let's say x squared over this guy, 0.0200 minus x squared. And all of that is equal to my K value, which is given. Okay, so now I can solve for that. That's pretty straightforward. The nice thing about this is that we have some perfect squares here, and so in solving for these things I can just take the square root of both sides. So take the square root, and that gives me x over 0.0200 minus x is equal to plus or minus 0.76. Now this is the key to taking the square root of things. Remember, with square roots, we can have two negative things that we multiply together that give us a positive thing, or we can have two positive things that are multiplied together to give us a positive thing. So we have to take into account both options, and both of these options are possible. So now I need to solve this equation for x equals, whether it's plus positive 0.76 or whether it's negative 0.76. So we end up with two values for x. Our x can equal, if we go the positive route, I got 0.0086. And if we go the negative route, I got negative 0.063. Okay, now I have to decide, in my scientific brain, with all of my rationality and my experience with chemistry, I need to look at these two numbers, look at the information that I'm given, and figure out if they're both possible. Which one is possible if either one of them? And usually in these types of problems, unless they're set up wrong, you're going to have one of these that you know immediately isn't going to work. Or maybe not immediately, but you're going to have to plug it in and you'll figure out that it doesn't work. So in this case, if I look at plugging x back into my equilibrium concentrations, which is what I'm ultimately solving for, that's what the question asked for in the first place, was to find these equilibrium concentrations, then I know that it can't be this one, because when I plug in this for x, that gives me a negative concentration of my products, and there's no such thing as a negative number of moles per liter, right? I can't have a negative amount of matter. So we know that this guy is not possible. So that means that my x has to be this one. So mathematically, the math tells me I can have either of these answers when I solve this problem. The chemistry, the applied part, the physical part, tells me that this is my answer. And so now I can say, well, my question was about the equilibrium concentrations for everything. So for carbon monoxide and my water, then I can plug that in. I plug the 0.0086 into my 0.02 molar, and I end up with 0.0114 molar. And then for my carbon dioxide and my hydrogen, then that's going to be just my X molar. Okay, so that would be my answer. Okay, so we did some algebra, we did our ice table, we plugged in values, and we ended up with equilibrium concentrations. All right, let's do another one. I know that you're already excited. Okay, so let's look at the reactants and products for these guys. We're going to see how much we have at equilibrium for these. My pen is drying up here. Let's try another one. So we're going to make our ice box. So our initial amount here is given. So I'm starting with 0.5 of each of my reactants. Not sure this pen is better. Might be worse. And I know that my product doesn't give me any information about that. So I have 0 concentration starting off. Now my change is going to be based on the molar quantities here. So I'm going down by X here, down by X here, up by 2X here because of this coefficient. And so my equilibrium concentrations are going to be the sum of those. So 0.5 molar minus X, 0.5 molar minus X, and then 2X. Now again, we can relate these equilibrium concentrations through the expression for K. So the K value is equal to 49.7. So my K expression is going to be the concentration of my products raised to the power of their coefficient over the concentration of my reactants. Oops, that's an I. And now if we plug in our equilibrium concentrations, we have a 2x squared over this quantity. So I'm going to do this times this. I'm just going to put it in brackets here. So let's just do 0.005 minus x, and let's do that whole quantity squared to save myself some room. And that is going to be equal to 49.7. Okay, so I can do the same operation. It's nice when I have perfect squares. We'll talk about in future videos when we don't have perfect squares and we have to break out the quadratic equation. But for right now, we have nice examples with perfect squares, so we can take the square root of both sides. We end up with 2x over 0.5 minus x is equal to plus or minus 7.05. Again, plus or minus on our square root here because we have a number value. It can be a negative number, mathematically speaking. So math tells us we can have 2 answers to this. So blame math. So now we have to solve this equation as if we're setting it equal to positive 7.05 and negative 7.05. So we end up with 2 values of x. Here's our x for one way, 0.39, and for the other way, 0.69. Okay, so now we have to evaluate, again, with our rational scientific brains, because we know that numbers have meaning in science and in applied kind of math here. So we have 2 potential x values. Which ones could fit in as equilibrium concentrations? Well, either one of them could fit into the 2x, right? That's going to give me a number that would be a concentration. That doesn't seem that unlikely. But if I plug this guy in, this one, into this expression, that gives me a negative number. 0.5 minus a 0.69 would give me a negative concentration, so we know that that is not possible, right? We cannot have a negative amount of matter per liter, so we are left with this one. And so this is my answer, and so I'm going to plug these in, and I'll get my concentration of hydrogen is the 0.5 minus my 0.39, which gives me 0.110 molar. The concentration of my iodine is the same because it has the same equilibrium expression there to figure out my concentration. And then the concentration of my HI is equal to 2x, which is 2 times this, which is my 0.780 molar. Okay, so we found our equilibrium concentrations. We used our ice boxes. We looked at a couple different examples and how this plays off math-wise. And if you have any questions on this, don't hesitate to reach out.